thanks everyone for coming to the my talk, and I thank JJ for inviting me and kind of giving me an opportunity to talk about my recent work in progress. So yeah, the title of the talk is the traction force microscopy for cells on high refractive index gel that has finite elasticity. So this work is totally done by my undergrad student, Sam Harman. He has been working with me for several years, and it has been very difficult to find a graduate student who has a good computation skills and also mechanics knowledge. Sam had kind of gave me great promise that by showing such skills. So it's still ongoing work. It's like a tremendous amount of work, but it's now getting some results. So I'm gonna share with you some preliminary results. But I hope this is a good time for just introducing what this traction force microscopy is and try to connect with you guys, and hopefully for some opportunity with further computations. Okay. Yes, so my lab is called Mechanobiology Lab, and the goal of the lab is to discover fundamental mechanisms behind mechanotransduction and cell migration using high-resolution live cell imaging and image data modeling and BioMEMS technique. So here, what we typically do is that we have this focal adhesion dynamics. I don't know why the movie is not playing. Yes, movie is playing now. Focal agent dynamics and traction force microscopy together in the same channels, same imaging. So one channel is dedicated to one of the molecules in the cell, and then the other channel is imaging the beads on the gel. And then using the bead images, we reconstruct the traction force traction map. And then this is focal adhesion protein called texillin. And from this channel, we segment and detect kind of diffraction limited spots, and then try to track them, and then try to see if this adhesion is kind of disassembling, can turn over in the middle of while they are red, or they become blue and black to mature. So using this, we kind of apply to many different aspects of the mechanobiology. One is ECM stiffness sensing. Cells are able to sense the stiffness in the extracellular matrix. How? So we try to apply this traction force microscopy and image analysis to show how what is the force transmission in between the adhesion and cytoskeleton and ECM, extracellular matrix, and what is the mechanism behind that. That's Nikhil's job project. And another one is endothelial cells shear stress sensing. So we build a shear flow chamber with a soft gel on the bottom and see how the force changes with and without the application of the shear flow. We apply, physiological shear flow or pathological shear flow and see how the force changes and also other molecules changes. And this is, kind of recently kind of new direction of the work that now, as we kind of try to improve the traction force microscopy, we want to apply to more fine structure of the cell protrusion called filopodia, and how when filopodia extends and retracts, how the force changes, those things we are applying. And also we keep improving this traction force microscopy. That's gonna be the topic. And also adhesion assembly, we kind of collaborate with kind of biochemists and see how the different molecules involved in the early adhesions are kind of involving different assembly level and different recruitment orders and traction forces. Also, this framework is great for the cancer mechanobiology because cancer, when it becomes malignant, they try to kind of exhibit more higher, resistance to the drug and also higher force. And this high force is involved in the resistance. So today we're going to focus on this TFM improvement because this is the seminar series for Center for Biocomputing and Digital Health. So what is traction force microscopy? So TFM is a soft-gel-based assay that we use to visualize the force field by a cell. How? So when we culture the cells on top of the glass, when cells contract, there should be a force, but we cannot visualize it because glass substrate is so hard. So we put the cells on the gel. So it should be soft enough to be able to be deformed by the force. So when cells, generate force, then there should be some deformation, but we cannot see that until we coat the gel with some fluorescent markers. So we coat the gel surface with the fluorescent beads, 40 nanometer diameter, and put the cells on it. So when cells contract, then also bead move to some certain level according to the kind of mechanics by the cell. So we image when cells are not there, the bead locations. And then when cells are there, also we record the image and try to compare the two. And then track these bead locations and get the displacement field. And then using our knowledge about the mechanics and also statistics, we reconstruct that into force field. So there's a general framework of what this traction force microscopy is. So of course, there are many usages since original development. So I'm going to show a couple of them. So first, this TFM has been used for cell migration studies. This TFM first used to migrating fibroblasts and show for the first time that front of the cell, for example, this region, there are large vectors of the traction force. And in the middle of the cell, there is not a big amount of the traction. And the direction was mostly inward. So that was for the first time found. And after that, people were studying how this force is related to the migration direction of the cells. So people found that when cells are just moving this way, and then if there's some high peak force and there's some other place, they try to protrude to that place. And then if there's another force peak there, there's another force kind of cell protrusion there. So try to kind of find that how the force and protrusions are coupled and direct each other. And also this force has been also studied with actin flow. So the traction was measured in the high resolution using very dense beads. And also they try to see in the front of the cell is called lamellipodia. And also behind there's a very focal adhesion dense region called focal adhesion region. And also behind it, there's a cell body region. So like depending on the location compared to the cell front, there's like some trend there where focal adhesion region has a high traction force, and the lamellipodia has relatively intermediate level of force. So they correlate those with try to correlate those with the actin velocity. Actin is the cytoskeleton that gives rise to the traction force when transmitted through something called focal adhesions. Here, using something called speckle microscopy, actin speckle microscopy, they were able to track the velocity field of the F-actin. And they found that, in the very front lamellipodia region, the velocity is great. And the focal adhesion region here, the velocity is kind of intermediate. And then cell body, the velocity is also very, very low. So they found, this, there's like not linear relationship between the traction stress and the F-actin speed. There's like more biphasic relationship. Also, this TFM has been used for overall cell contractility measurement. So this is one interesting work by Cindy Ryan King in Vanderbilt. And yeah, they use many cancer cell lines, using kind of benign cancer cell lines from the breast cancer cells, prostate cancer cells, and also try to use the malignant cell line in the breast cancer cell, prostate cancer cell. And they found that all these malignant cells, metastatic cells, showed greater amount of attraction than benign cancer cells. So somehow those are related, they advocate. Also, this traction force has been measured to study stiffness sensing, as we were doing also. So here, cells were micro-patterned to a circular shape and use a different level of the kind of stiffness and try to kind of reconstruct the force, measure the force, and they found that there's an increase in traction stress according kind of up to like 16 kilopascal of the Young's modulus. And then it stays there at the higher stiffness regime. So, and then they found that cell area is important for the overall traction force. So such overall cell contractility measurement, yeah, for those, yeah, this traction force microscopy has been used. Later, this force has been also tried to be linked with cell-ECM adhesion. ECM means extracellular matrix again. And here, this TFM's spatial resolution becomes matter more. And so in this case, this is a little bit while ago, these authors try to see how zixin, one of the molecules involved in the adhesions, are related to the force. So they found that when there is like this initial appearance of this zixin molecule, there has been large force involved. And then when it becomes more interior part, slide into the interior part, this large force is gone. So that is kind of like very first finding about the new focal adhesion and the force. So it was like very interesting, but later on, people also try to do same thing. In this case, penicillin, or one of the other focal adhesion proteins. And then they found that when focal adhesion appear, there's like only incremental force increase there. And then as this focal adhesion kind of get matured, there's a higher and higher force. But as you can see here, this force resolution was not very great. There's like a lot of smoothing going on. So we really don't know if this force is really from this adhesion, but some kind of effect from other adhesions and other places. Later, people other scientists were trying to improve more, this resolution, try to see how the force changes over time for the stable adhesions and the adhesions at the edge of the cell. They found that when adhesion is more inside, this focal adhesion, the traction force is more stable, kind of not fluctuating much. But here, when adhesion looks not very fluctuating, but force becomes fluctuating more. So these authors try to relate this effect or phenomena to stiffness sensing. So those things, I want to point out that this resolution, with a higher resolution, higher accuracy, we can do more greater finding about how cells sense the force and stiffness. So the key question is, what determines the traction force microscopy resolution and accuracy. So the factors we thought about it is the marker density. So if we have, denser markers, then definitely we can have more reports of the traction, displacement field, so that we can have better resolution. And also, if we track these markers better, then we can have better, kind of accuracy. And if we can detect these individual particles better, then definitely more accuracy there. And mechanics and inverse problem, they are all involved. If we know this gel mechanics better, then we can infer better. And if we solve this inverse problem better, then we infer better traction force distribution. So those are the vectors. So I'm going to talk about only a few of them. Let's say inverse problem and mechanics, and a little bit of tracking. But we are also working on other kind of parts at the same time too. So this from here, my kind of participation into this traction force microscopy world is by contributing to this inverse problem solution. So in this audience, in the engineering community and also statistics community, L1 regularization is so common probably, but in the cell biology community, it was not very common. So my contribution to traction force microscopy, 7 years ago, was through kind of applying this L1 regularization into inverse problem solution involved in the TFM. So for the inverse problem solution, the regularization is necessary, as the solution to the inverse problem is ill-posed. So for example, if you have this equation, m is a forward map and beta is a force, then we can get this displacement. This is for solution. But the problem is that we want to get the beta out of u and m. So then this m should go to the right hand side. If you cannot directly inverse that because m itself is ill-conditioned. So what you do is that we try to solve this minimization problem to find the beta that minimizes this measurement error versus and also we penalize force coefficient with some constant called regularization parameter. So when we penalize this beta, we use some norm. We can use the L2 norm, then it's called L2 regularization. If you use L1 norm here, then it is called L1 regularization. So what we showed is that in the TFM application, if you use L2 regularization, it produces systematically underestimated traction or noise amplified traction. So what we have done is that what I have been done is to create some ground truth force field and try to kind of have these large forces by the large focal adhesions and a little bit intermediate force level with the force focal complex, and also nascent adhesions, kind of small adhesions with a small force level with a small area. And then try to kind of produce the calculated displacement field and also apply that into the synthetic bead images, and then track the displacement again using particle image velocimetry, and then use this L2 regularization to see the similarity to the original force field. So this is the outcome. So when we use very conventional L2 regularization with L corner, something called L corner regularization parameter, then we see systematic underestimation. So if you maybe enhance the contrast of this range, then we'll see more smooth force field, but overall force level was diminished. And also we don't see this nascent the force from the nascent adhesion a lot. So it's all kind of smoothed out. But if you use a little bit less regularization parameter, yes, we can rescue some of the magnitude effect. We can have the larger magnitude, but also we see some force peak there, but also it amplifies the other vectors from the measurement errors. So we don't know if this force is from the adhesion or some regularization artifact. But if you use L1 regularization, it has great characteristic to force the sparsity, the solution to be sparsity. So it really minimally underestimates the solution. So it kind of suppresses all the background level. And then while it kind of does not underestimate the force, so we have better resolution on this nascent adhesion level. And also we have overall better magnitude for the focal adhesions and focal complex mimics of the large forces. So that was my contribution published. And so using this, L1 regularization, we can detect the force that has lower magnitude with kind of less size, so that the yellow area we can get more. So that was the contribution. And also after coming here, we try to do better kind of improvement of the tracking part of the traction force microscopy. So here we showed that existing tracking method fail to track extremely large displacement. So this is actually shown in the experimental side. The ground truth, we have this large force, and then we calculate this is ground truth displacement field, and apply that into the synthetic bead images again. And we use a conventional PIV, particle image velocimetry method there, and also correlation-based PTV method. But they all fail to get this the displacement field at the large displacement region right. So we devised some of the algorithm to kind of use the neighbors to retrack fill in the large vectors. So I don't show the algorithm flow chart here because this is not the focus of my talk today. But just to show that the progress so we kind of start from the confidently measured displacement field first, and then we try to fill in what was missing, and then there's like some cross correlation involved and comparison with the neighboring vectors involved. But the basic rationale is that this force, these vectors needs to be at least similar to the neighbors. So by doing that, we can also have larger vectors filled in this missing region, which is definitely not perfect, but it's actually better than not having any information. So that is being reviewed right now. So now this is the main talk, okay? So I'm gonna be very fast because I don't have a lot of data for this work, but I'm gonna show you some framework. This high refractive index, so for our traction force microscopy, we use a soft gel, as I told you before. And we use something called high refractive index gel. Why? Because it supports total internal reflection. So in the normal cases, when we use the total internal reflection, we use only cover glass that has refractive index of 1.52. So since cell and cell culture buffer has much lower refractive index, there's like total internal reflection kind of happening in the interface between cell and the glass. Yes. But usually, if you use a gel that has, also 1.3 something, then total internal reflection happens at the gel and the glass interface. But if you use some special silicone gel that has very high refractive index, 1.49, there's not much refraction going on here, but total internal reflection is happening between cell and the gel, so that we can see the cell and the beads at the same focal plane with a very high signal to noise ratio. So this is an example. So if you use the just epifluorescence and then see the actin, then we have all the actin fibers and some, this, non-specific signals we see. But if you use a TIRF, we can really see the actin that is near that interface. So we almost see the focal adhesion-like actin there. And also at the same focal plane, we see the bead images, beads there. So using beads, we can reconstruct, we can, compare with the beads when cells are gone. Then we, have this displacement field, force field, and try to correlate the force field and the actin together, something like that. So that was the great promise that it gives us the better quality of the image. So we wanted to keep using this high refractive index gel. So to do that, we want to really quantify the mechanics. Before going there, we kind of learned that this elastomer has something called, something called finite elasticity. That's typical for elastomer and biological material. So we know that brittle polymer or steel or anything elastic shows like linear response between the strain and stress. And also some plastic has some plastic deformation there, but elastomer has some S-shaped behavior. There's like some increase and flat region, kind of flat, but also strain stiffening going on there. So maybe since this gel, high refractive index gel, is also silicone based, so it's also elastomer. We might have to use different mechanics rather than linear mechanics. So there are some, I'm showing you some typical finite elasticity model. Usually this nonlinear elasticity is formulated via strain energy function. So there's a Mooney-Rivlin reduced polynomial and Ogden and Fong level. And this I1, I2, they are stress, invariant. Yes. So I'm not going to go to detail. So what we do is that from here, we try to measure this mechanics, but we couldn't do the tensile testing because this gel is very sticky and very, very soft. So couldn't really make the dopant shape sample, but we used the AFM with collaboration with Fei Long in mechanical engineering department. And we tried to kind of, at that time, we didn't know, maybe it shows the nonlinear mechanics. So we used a Hertz model. And, in the Hertz model, there's a contact point important, right? So if you use very early contact point, then, this Hertz model failed. Only when we use something here, the contact model, this Hertz model was perfectly fit, but already we missed all this early point there. Okay, so we thought, or maybe we had to use different model. There was one of the nonlinear model called Ogden model. So if you use here very early contact point here with this earliest Ogden, Ogden fit, it really lead to the perfect fit there. So with R square value like 0.99. So it was, and then only when we have like very unrealistic contact point, it start to kind of deviate. So this was fitting this AFM curve very well. So we had a little bit more confidence about this nonlinear mechanics about this Q-gel, which is the non-high refractive index gel. So we want to involve this nonlinear mechanics into the traction force microscopy pipeline. So usual pipeline is that we start with these bead images, stressed and unstressed, and then we get this displacement field. At the same time, we also get some gel mechanical properties like Young's modulus. For the nonlinear mechanics, we have to have, initial Young's modulus and some nonlinearity parameters like alpha. And also we have to have the bead locations to map out the forward map to the location. And so using this measured displacement field and forward map, which I'm gonna talk about in the next slide, we solve the inverse problem. Then we get this force field. So that's a general pipeline. So for the forward map, we use, before this nonlinear one, we use an analytical solution called the Boussinesq solution. So it has totally, there's like an analytic solution. So we just convolute that. Then that's no problem. But in this nonlinear regime, we had to use FEM. So Sam used the FEM solver. So like initially we were trying to use only MATLAB to use this PDE toolbox. But since it becomes a more nonlinear, MATLAB didn't have a good function we can use. So we went to FE Bio and Gibbon, that is wrapper kind of MATLAB interface to use the FE Bio functions in the MATLAB environment. So we did everything in MATLAB, but used the libraries given by the FE Bio. So here, so 4 steps are involved. The force mesh. So we create first the force mesh. So we use the grid points, regular grid, and then at each grid we have this pyramidal shape of the basis function, and then we place this basis function on top of the domain, our spatial domain, to solve the displacement field. And then we solve this displacement field in the space domain. So we have to have the mesh. So we have the more finer mesh in the center so that we have better resolution. But after getting the solution, we try to interpolate to the bead location, which is not necessarily at the same place as this mesh's node places. So we kind of interpolate them into the bead location so that we can create something called forward map. So forward map is a giant matrix that has the solution to each basis functions forces kind of displacement solution there. So for force into the x direction, we have fill in one column here, and force into the y direction, we fill in another line here, a kind of column here, and then we kind of fill in everything there. So it becomes like 2n by 2n to m matrix there. So we want to inverse that in the inverse problem solution. I want to show you what is this FEM based force solution. And there is this Ogden versus linear solution for tangential force application. So what we did was that we applied the tangential force. So let's say this is a domain from 0 to 512, and then only from -5 to 5, which is at the center, we gave this pyramidal shape of the force. This is just 1D representation of the 1 Pascal peak, okay? And then calculated the displacement profile using linear analytical solution called boundary element method, fast BEM, or nonlinear FEM there. So here we show that we use the same Young's modulus and to be the initial modulus for this nonlinear FEM. And we show, yeah, there's like peak difference there. But if you go to this right, there was like cross there, this nonlinear FEM solution has, higher, level of the displacement if you go to the, like, apart from that peak. Yeah. So then it kind of shows that the Ogden solution, which is nonlinear, is more long range. And then at the center, it is more short, it is more less peak there. So we don't know how that will impact the inverse problem solution. So we try to do some simulation study. So in this simulation study, as you saw before, so we had this ground truth force map up to 500 Pascal, and we had this ground truth displacement map up to like 10 pixels. So in terms of the micron, it becomes like 1 micron or so. So here, from here, we try to calculate, use this displacement map directly to get this apply different force reconstruction technique. One of them is called FTTC. It's called a Fourier transform traction cytometry. And it showed amazingly good, localization there. A little bit of, this bump there, but it was good. And also, if you use the FastBEM, it showed also pretty good localization. But there's like some side effect there, some dots there nearby. If you use a linear FEM, then there was like more kind of side lobe there, lobes there, but it also showed a good localization. And if you use a non-linear FEM, also it has a good localization there, but there's like a little bit of side lobe there. Okay, some smooth lobe phenomenon. So if you cut half in the center line horizontally and see the solution into the y direction, we see there's like kind of this nonlinear FEM showed this one has like more higher peak there, but also it has side lobes. Also, if you quantify the deviation of the traction magnitude, there was like less, deviation for the nonlinear FEM based TFM, but also while this FTTC is that you solve this inverse problem, linear inverse problem, using the frequency domain. Less there's underestimation from this FTTC. So so this doesn't kind of tell us the exact accuracy of this nonlinear FEM based force map. So we try to apply this into the experimental bead images, and it was very hot and fresh, so we couldn't get the entire solution. But we showed that FTTC, FSBEM, linear FEM showed a kind of comparable, the force map from the experimental bead images here. Nonlinear FEM is being solved right now, so I cannot show you, but yeah. But the best thing I want to tell you here is that this nonlinear mechanics framework has been incorporated into our TFM framework. Currently, this something called TFM toolbox or a package is being used worldwide. There has been many citations about this method, this software, and surprisingly, the linear mechanics, as you see in the simulation studies, can still predict the force distribution very well. And we have some ideas about why. And the current attempt implicates some necessity to improve this inverse mechanics scheme, actually. And this framework can be used for the future, TFM development in 3D and topological substrate. that is kind of more bigger picture, you know. Since we now can involve many different mechanics, now we can apply to the topological substrate, fibers, or fiber environment, or 3D environment. That is the future goal, and then yeah, future dimension. And the future work is that, you know, we want to find cases where the deformation level is very large, so that it can show, because like this nonlinear mechanics shows some more distinct differences when deformation level is large enough. So we want to find this case more systematically and then show that. And also we want to compare the Ford method that does not need the regularization. So currently we are using, you know, this regularization. We build the Ford method and do the inverse problem solution. But there is a way to, you know, just directly apply this mechanics from, you know, from the displacement to the strain, to stress, and to traction. So those reconstruction can be also done. So we want to compare that with those direct methods. And this is a future idea. So can we, you know, so since we are using, you know, this fluid mechanics knowledge, solid mechanics knowledge to do this TFM work, and also the statistics. But can we do it using deep learning? So that is the kind of future idea that I want collaboration with someone. So can we educate the neural network to do the better tracking of the beats? And also, can we also educate the mechanics to the neural network to reconstruct the force directly from the beat images? Or can we do the better inverse problem solution using, you know, this neural network? So that is the one thing that I want to share. So that's it. I'm sorry for the very short amount of the result. I'm very sorry. I just want to have the discussion with you guys. So I thank my lab members. You know, again, this Sam is the guy who built this framework, and all other guys, you know, Nick, Mohanish, Shayna, Caitlin are doing the experimental work using the traction force microscopy. I also acknowledge my funding source from NIH, and also Sam has been awarded with the SURF and URIP from the MTU. So and also I acknowledge Fei Long and Faith Morrison for their generous, you know, collaboration with their equipment of AFM, and also what is it, the microrheometer. Thank you. I will be happy to answer any questions if you have.
Dr. Han, I have a question for you about.
Oh, thank you.
Yeah, it's very nice talk and really interesting. So this here, your model can be used to study different cell phenotypes, or just limited to the cell type you use here?
Yes, yeah, we can use all different cell types, you know, amoeboidic cells, you know, cancer cells, you know, fibroblasts, epithelial cells, endothelial cells, any type of cells, if they are adherent, you know, then yeah, just except for the red blood cells, probably, yeah, we can use, yeah.
Okay, so the key point is the cell can adhere to the substrate.
Yes, yes. Yes, we coat fibronectin or any, you know, ECM proteins on top of the gel. So you can also functionalize the gel surface with different molecules, you know. So for platelets, you know, people use von Waldorf factor to activate those, encourage the adhesion of this cells, platelets. And yes. Okay. People use collagen, fibronectin, fitronectin, yeah, any other ECM proteins.
So if if it's not gel, like it's a kind of larger span scaffold and attached on the gel surface, and then examine the cell, like cell size or growth morphologies upon with response to the forces. Do you think it's possible, if that scaffold is not thick, just very thin, and still can be observed, and your design microscopy?
Yeah, so it depends on the level of the deformation, definitely. So if it's, even if, the gel we are using is kind of like 14 micron thick. So I don't know if your coating, but if it's like just, less than 1 micron thick, then I don't think there will be deformation. We can observe visually. So I encourage to kind of coat that specific molecule or something on top of the more kind of elastic gel that we know the elasticity. Then we can measure the force. Yes.
Okay. Okay.
Yeah.
Thank you. Thank you very
Yeah.
much.
Yeah. Thank you for the question. Yes.
Sangyoon, I have a question. I don't know whether you can hear me okay.
Yeah, I can hear you. Yes.
So you have that governing equation, which is m beta equal to u.
Yeah.
The m for me is more like the flexibility method we use in the mechanics. When you do the nonlinear mechanics or nonlinear finite modeling, why not you just use that the displacement control finite element method instead of using the flexibility control method? I'm just curious to see is there any reason for you to do that.
Yes, yes, that is exactly the future work probably that I want to do that. The rationale so far not to go to that direction was since, as I showed you before, this problem has been very ill-conditioned problem.
Mm-hmm.
So it's kind of, we know that force convolution of the forces give rise to the displacement. But if you enter the displacement as an input, then such deconvolution effect we cannot maybe solve. So that was the main thing. But maybe I have limited knowledge, so it's probably worth trying a shot to see what happens. So that's a very good comment, I think. Yes.
Okay, I think in the limited time, we probably have to conclude here. Saying we will talk offline. I think we have a lot of overlaps in terms of what we do, so we can talk
Yes.
offline about that.
Of course.
Okay, let's thank Dr. Han one more time, and it's he delivered an outstanding talk. So
thank you so much. All right.
Okay, that's it. Thank you, guys.
Thank you. Yeah, have a good one, guys. Bye, JJ.
Bye.